Quantum computers promise to solve problems today's machines can't touch. They don't just work faster, they work completely differently. That difference comes from a world where the rules themselves break down. Particles can exist in multiple states at once. They can be separated by vast distances, even across galaxies, and remain mysteriously linked. And simply observing something changes it. So, what happens when we learn to harness that kind of power? And how does quantum change how we see reality? Hi, everyone. I'm Lynn Toman, and this is Three Takeaways. On Three Takeaways, I talk with some of the world's best thinkers, business leaders, writers, politicians, newsmakers, and scientists. Each episode ends with three key takeaways to help us understand the world and maybe even ourselves a little better. Today, I'm excited to be with Andrew Houck. Andrew is Dean of Princeton's Engineering School and a professor of electrical and computer engineering. He runs one of the world's leading quantum computing labs. His work sits at the frontier of what's possible. And he's building computers that harness the strange rules of quantum physics to solve problems classical computers simply can't touch. He and his team are working on everything from quantum algorithms to the materials challenges that make these machines so difficult to build. He's working to take quantum computing out of the lab and actually make it work in the real world, where it can be used to potentially design new drugs, create new materials, protect data, power AI, and even potentially give us a new reality. If you've ever wondered about quantum computing and what it means for the future, Andrew can explain it. Welcome, Andrew, and thanks so much for joining Three Takeaways today.
Thanks so much for having me here.
It is my pleasure. When people hear quantum physics, they often imagine something mystical or sci-fi. What is it actually in plain English?
So, about 100 years ago, scientists started realizing that the world did things that were unintuitive, counterintuitive. We formulated a set of rules that could describe that weirdness. Objects could be more than one thing at the same time, like a cat being both alive and dead. Observing something seemed to change a system, and you could form links between particles that were distant across the universe. Those all were surprising. And so that led to a lot of creativity about what quantum could mean. But it's still a set of rules. And so it's both nothing like what you would expect and also very constrained by a set of rules.
And these strange quantum rules are rules that govern the universe at the smallest of scales.
Well, they show up at the smallest of scales. The reason you don't see them on a day-to-day basis is you don't have senses that can perceive atoms and electrons. It's just as weird that when you let go of something, it falls to the ground. Why should gravity exist at all? You don't question it because you're used to it. Quantum mechanics is kind of the same way, except scientists only first started observing these phenomena 100 years ago.
And what was the first quantum result that made scientists themselves say, wait, that can't be right?
There were a number of things that shocked people. I would say most famously, Einstein objected to this idea of entanglement. That is, that particles could be linked over distances, because relativity says information can't travel faster than the speed of light. That's still true. Entanglement doesn't let information travel instantaneously, and yet there is some instantaneous linkage between particles.
And that instantaneous linkage between particles can be across vast distances, even across galaxies.
In principle, yes, you could have that over arbitrarily large distances. And that's one of the key pieces for building interesting quantum technologies.
What are the other key pieces?
So the others are called superposition This is the idea that an object can be more than one thing at the same time. For a computer, we store information as zeros or ones, but a quantum computer could store information as zero and ones at the same time, and that allows you to explore a much larger space in your algorithms. And this idea of measurement. When you look at a system, you only get one outcome and you change the system. And that's instrumental for doing error correction and for sort of collapsing patterns in data.
Can you explain that a little more?
Sure, when you observe a system, you only ever get one outcome. So if I ask just the right question, then the system, which could have been sort of in a superposition of everything that ever could happen, suddenly becomes only a subset of those things. And that allows you to sort of search for patterns in data, periods, uh, periods where something repeats over and over again. These kinds of things are often the things we're looking for when we run some kind of algorithm. It's also important for error correction. In quantum computing, information is very fragile, and you can get these very small analog errors that are very hard to correct. But you can ask the question, did an error occur? And as a result, you get the answer either yes or no. And if you get a yes, it makes the error much worse, but also something that we can fix.
So, quantum allows many different possibilities at once. The famous case of Schrodinger's cat being both potentially alive and dead at the same time.
That's right. So Schrodinger's cat can be both alive and dead at the same time. But when you look at the cat, you only ever see a cat that's alive or dead. But until you look, it can be both. And that's different from not knowing maybe it was alive or maybe it's dead. It's actually something different, that it has some elements of both.
So, how does this quantum rule that things can be in multiple states at once until they're observed help to create incredibly powerful computers?
So often when you're using a computer running an algorithm, one of the things you're trying to do is search for a needle in a haystack to explore some vast possible set of numbers that might be the solution to your problem. If you have a quantum computer, you can start by putting in the computer in the superposition of every possible input you could ever want to put into that algorithm. And that allows you, in some way, to get every possible answer in some state. The problem is, as soon as you look at it, you only get one answer and it's randomly picked, and that's not very useful. But this sort of large, before you look, the cat is still alive and dead state contains information. And if you look at it in just the right way and ask just the right question for certain problems, something very interesting can pop out.
So interesting. And Andrew, you're not just studying these strange behaviors, you're using them to build computers. What makes these weird quantum computers so powerful?
Quantum computers are the only different kind of computer that's ever been invented. For a long time, everybody thought every computer that existed was the equivalent of a Turing machine. This is the way computer scientists think of computing. And that means they can all solve some problems and find other problems very hard. Quantum computers work differently. They don't just make each step of a problem go faster, a faster processor, or more memory. They can solve problems that we don't know how to solve in any other way because they're fundamentally different.
And how are these quantum computers different from the laptops and phones that we use
Mm.
every day?
So the key thing is that the part that stores information has to itself be quantum mechanical. It has to be able to exist in these superpositions. It has to be able to be entangled. It has to be able to obey these weird rules. And that means that it needs to be isolated from the world around it so that we preserve its quantuminess. That's also a challenge. You also need to get in there and have it do something, right? It can't just be completely isolated. Otherwise, your computer just sits there and you can't run any programs. And this tension between needing to be able to quickly run a program, but also have it be isolated from the universe is why they're so hard to build.
You've said that quantum computers don't just work faster, they work differently. Can you explain a little more about what that actually means?
Sure. So, one way that we think about how hard a problem is how many steps it takes to solve. If I have a regular computer that gets better, it still takes the same number of steps to solve, but it can do each step faster. But if the number of steps to solve is some, enormous number like the number of atoms in the universe and each step is a little bit faster, it's still not going to be able to be solved. It's just never going to happen in the age of our universe. The way quantum computers work is by shortening that list of steps. They work differently, and so problems that can only be solved one way on classical computers take just fewer steps. And so that is what makes it possible to solve things in relatively short timescales that we just don't know how to solve in any other way.
Some exciting potential ideas are using quantum computers to discover new drugs or new materials or more efficient ways to create energy. Why can't normal computers do that? And how could quantum computers completely change the game?
So a lot of times we're thinking about simulating systems that involve atoms and molecules and electrons, and those themselves are quantum mechanical objects. And so you're usually trying to use classical things to represent this vast quantum superposition space. And that's incredibly inefficient. The idea of simulating systems that are themselves quantum mechanical with a quantum computer is essentially trying to use something that can natively think in a quantum way and therefore might be able to more efficiently get to the kinds of solutions we need.
Because it can look at a much wider range of possibilities.
It can look at a much wider range of possibilities. And for those problems in particular, for things involving drugs and materials, it just speaks natively in the right language, right? Those are quantum systems. And it's very inefficient to describe a quantum system without using a quantum system to represent it.
And those are quantum systems because they exist at the levels of atoms and molecules,
That's
which is the
exactly
language of quantum.
that's exactly right. Those systems exist as atoms and molecules, and the language of quantum was developed to describe the world at that level.
And what could quantum potentially make possible? You mentioned medicine, energy, materials.
We don't actually know what quantum computing can do with certainty. There are a few things we can prove. We know they have real implications for cybersecurity. We believe that you can simulate quantum systems much more efficiently on them. But a lot of our best algorithms that we run on computers are what we call heuristics. We run them, they give us answers. Those answers are things we didn't know. We can't prove they're optimal, but they're better than anything we had. And there's a lot of reasons to suspect that quantum computers will have vastly more impact in these heuristic kinds of algorithms than in things where I can prove down on pen and paper that it will take exactly this many steps to get an optimal answer.
You mentioned encryption, and some people worry that quantum computers could break all current encryption. How real is that threat?
It was a fear a few years ago. So certainly quantum computers can break the problems that underlie older forms of encryption like RSA. That's definitely something we need to worry about. Fortunately, in the last year, NIST released new algorithms for what we call post quantum cryptography. These are things that are based on mathematical problems that we think are also hard to solve on quantum computers. Quantum computers can't do everything. And if we move to that form of encryption, then everything should be safe, even if somebody does have a quantum computer.
So, quantum physics potentially allows for communication that can't be hacked.
So there are two different things, actually. So there's quantum communication, and this is communication using quantum particles that is provably secure as long as the laws of physics as we know them are true and you implement things correctly. Often something is secure in the main channel, but there's ways in which you mess things up. There's also what's called post-quantum cryptography, and that runs just like any regular cryptography. It's just a software running on a classical computer, but it uses a problem that quantum computers can't solve, and therefore it remains secure even if you have a quantum computer.
What makes quantum computers so hard to build? Why can't we just scale them up today?
Now, there's all kinds of challenges there. You need to start with something that can actually behave in a quantum mechanical way. And the leading platforms either use single atoms or single ions trapped, floating in vacuum, held in place by lasers or electromagnetic fields, or superconducting circuits fabricated like the computer chips we have today. The challenge is in the circuit models where you can build a lot of them, the information is incredibly fragile. The very first superconducting qubit that anybody built, a qubit is a quantum bit, something that can store quantum information. The very first superconducting qubit somebody built lasted for 1 nanosecond. You can't do a lot of computation in a nanosecond. In the 25 years since that time, we've gotten that number up just recently above a millisecond with work that came
In
out of
your
my
lab.
lab in collaboration with my colleagues here at Princeton. So it's very exciting to break a millisecond. And that's long enough that you can start to do error correction and think about actually getting real algorithms done. But there's so many things that can come and destroy this very fragile quantum state. So it's hard to get to the point where you can do a lot with it.
So even an elevator moving in another building can disrupt a quantum computer?
It depends on what your system is sensitive to, but if you're sensitive to magnetic fields, elevators are a real problem. Vibrations are a challenge for a lot of these systems. So you need very carefully vibration isolated systems. You need to make sure the temperature is absolutely controlled. And then we also care very much about materials purity. What are all of the atoms that shouldn't be there that are around your material? All of those things come and hurt you. And every time you make your qubit 10 times better, that means you're more sensitive to all of those things that didn't matter before. And so every time you make it better, every little thing that didn't used to matter now starts to matter. So you just increase the number of problems you have to worry about.
Looking ahead, what excites you most about the potential of quantum computing?
I've been working in quantum in some form or another for more than 25 years. I want to see a quantum computer do something that we can't do on any other form of computer. I don't even care what it is at that point. I want to see one of these things work. We've been working at this for so long. And the way I'll know it happened is, I want to see somebody write a paper and I want someone to care about the answer that the quantum computer gave. Not because it was arrived at on a quantum computer, but because it's an answer that they actually wanted to know. And that's never happened.
And how about designing new drugs or new materials or new energy efficient
Yeah,
systems?
that's right. The reason this field is exciting is that you get to play with the mysterious world of quantum physics, the great wondrous way the universe works, and also build something that can be applied. And maybe we'll do something that actually helps humanity. Princeton's motto is Princeton in the service of humanity. And we really care about doing things that matter. So the scientific nerdy part of me just wants to see the physics work. And of course, working to build a new drug or to make a new catalyst that can help with energy and in the environment, something that actually helps mankind would be wonderful.
We've talked about the weirdness of quantum. Does quantum physics change how you think about reality itself?
I mean, people have thought about the philosophy of quantum mechanics forever. And what does it mean that we have these rules? The way that most physicists think about quantum mechanics in an operational way is this idea of superposition and measurement. And that, I think, doesn't fundamentally make sense as a philosophical worldview, but it works. People sometimes refer to it as shut up and calculate in terms of the way you interpret quantum mechanics. Everybody knows it probably doesn't work quite like that, but it's the most practical. This idea of what does it really mean to have something that is in more than one state at the same time and measurement changes it, that does get me thinking about how the universe works. Because what I think actually happens when you measure something is that you enter that superposition. The thing that does the measurement then becomes part of the superposition, and the superposition just grows and grows and grows. And that's kind of mind-breaking trying to figure out, well, then what does that really mean? And so, you often just go back to, okay, well, I'll do the math and I know the answer and this all works and these set of rules can predict things. But it's philosophically not satisfying.
Before I ask you for the three takeaways you'd like to leave the audience with today, is there anything else you'd like to mention that you have not already talked about? Andrew, what should I have asked you that I have not?
um, One thing that I think is really important about the whole field is how the different pieces work together. We have quantum computing companies, we have national labs, we have academics, and they all work on different parts of this problem in ways that spur productivity forward. Industry has these incredibly large scaled systems that I could never build in an academic lab with the size of investment that we make there. We in academia make these breakthroughs that make it so much easier for these systems to scale. We think of the crazy ideas that suddenly, when they work, change the way everybody thinks about the field. And the national labs have these incredible tools that are, billion-dollar ways of probing materials that are essential for figuring out all of the problems that exist in the materials layer of things. And one thing that's happened under the National Quantum Initiative Act over the last 5 years is that these groups have come together and used their relative strengths collectively to advance quantum science.
That's wonderful. I think that's one of the themes of our world today, that connectedness leverages all the synergies.
Yes.
Andrew, what are the three takeaways you'd like to leave the audience with today?
Three takeaways to be left today. One, quantum mechanics is weird and mind blowing, but also follows a very specific set of rules. Two, these rules allow us to build entirely new kinds of technology that can solve problems that we can't solve in any other way. And three, we are actually getting close to these technologies being a reality and having a practical impact. We're not there yet, but sometime in the next few years, they are actually going to be making a real difference in the world.
That is so exciting.
Thank you so much for having me.
Thank you, Andrew. This has been a pleasure.